What if you could predict the entire structure of a crystal just by knowing how it repeats? What if atoms don't just sit, but follow a hidden order, governed by rotation, reflection, and symmetry? In this episode, we'll uncover how rotation, one of the most intuitive symmetries, helps us decode the elegant pattern inside crystals. We begin with a simple object, Suzanne the monkey. Watch what happens as we rotate her around the z-axis. No matter the angle, the motion follows a clear mathematical rule. Now, imagine two identical objects. One is the original. The other is generated by a twofold rotation around the z-axis. They move together, and notice. Their xy coordinates change, signs flip, but the z-coordinate stays unchanged. That's the essence of a twofold symmetry. Rotate 180 degrees, and the pattern repeats. Let's get analytical. In a plane, rotating a point by an angle theta adds theta to its original angle phi. We now move from visual to mathematical representation. Using this relation, we derive how the new coordinates depend on cosine and sine of theta. It's the foundation of all rotation operations in crystallography. The general rotation matrix around z-axis looks like this, with the theta symbol is suppressed. It transforms xyz into a new point rotated by theta. If theta equals 180 degrees, or pi radians, cosine theta equals -1 and sine theta equals 0. The matrix simplifies and clearly shows that x and y flip signs, z remains the same. Let's summarize the twofold symmetry elements in the P222 space group. Identity, x, y, z. Twofold around x, x minus y, minus z. Twofold around y minus x, y minus z. Twofold around z minus x minus y, z. Each rotation gives an equivalent atomic position in the unit cell. Here, Suzanne shows a fourfold rotation, 90 degrees at each step. There are now 4 positions, each 90 degrees apart. Track the xy values, not just the numbers, but their signs change predictably. Using the same matrix form, but with theta equals 90 degrees. The rotation becomes a powerful tool to calculate equivalent positions under fourfold symmetry. In group P4, for operations generate 4 equivalent positions. X, Y, Z, minus Y, X, Z, minus X, minus Y, Z, Y, minus X, Z. These match the Wyckoff positions listed in crystallographic databases. Now let's go hexagonal. A sphere rotated every 60 degrees around the z-axis fills 6 equivalent positions, a 6-fold rotation. But wait, the coordinate system also transforms. Hexagonal axes form 120 degrees angles. An equilateral triangle emerges, allowing us to read off new coordinates graphically. Let's track how x and y positions change under this hexagonal rotation. Each image shows a projected and schematic version, both in Cartesian and hexagonal systems. Notice, despite the name, the hexagonal unit cell itself is not a hexagon. But the overall tiling pattern, viewed as a lattice, is hexagonal unit cell. Here's the 6-fold rotation matrix, same form as before, but with theta equals 60 degrees. Multiple 6-fold operations can be combined. Rotation by 120 degrees, 180 degrees, and so on. This explains how higher-order symmetry emerges from simple repetition. Let's compare the computed positions with the official Wyckoff table from space group P6. They match. The diagram based on the equilateral triangle helps visualize every atomic equivalent clearly. In summary, identity. 6 superscript 1, 6 superscript 2, 6 superscript 3, each at 60 degrees. Every step produces a predictable equivalent position. Rotation symmetry is more than geometry. It's the key to unlocking the invisible regularity of crystals. In this episode, we explored the magic of rotation. But symmetry doesn't end here. In the next episode, we'll go deeper into mirror planes, inversion centers, and space group combinations. Because in crystallography, symmetry isn't just aesthetic, it's predictive. Stay tuned.